Hello and welcome to Quantum IAS. In this video lecture, we are going to study the second lecture of electricity and magnetism, or lecture number 30 of paper 1. Okay. So in this lecture, we are going to study these topics. Now, what I have written here, the energy of system of charges, because this was not written in the previous lecture, right? But I have taught you there, right? Refer to lecture 29, right? So we have discussed about the potential energy of the system of the charges, right? So it will not be dealt here. Okay. Now next one is the multipole expansion of scalar potential. Now we know that if we have a charge configuration, right, and if we wish to find the potential at a very large distance, infinite distance, so what we say, that we can treat this charge configuration as a point particle, right? Now the question arises, if the total charge q is not zero, then we can find something negligible here. That is for sure, because it is so large distance, infinite distance you can say, right? But is it the case if q is zero, we will get zero potential here or not, right? This is our prime aim in finding out the multiple expansion of this scalar potential, and then we will find out the concept, the origination of the dipole, right? Dipole moment, right? Monopole moment, quadrupole moment, right? So we only focus on the dipole moment and monopole moment. Quadrupole, we have a certain brief introduction about that we will see, right? Next we will see the method of images and its application, right? So these topics are very important, they ask frequently. Potential and field due to a dipole, I think you know these things, potential from your earlier classes also, right? So what I expect that you are having a good foundation understanding or conceptual clarity up to class 11th and 12th level, right? So if you have that, you will not find any difficulty in the remaining topic of dipole, right? They are similar to that. Okay. Now, so this we are not going to cover in this lecture, we have already covered this, right? Two types of energies, interaction energy, self energy, right? These things we have already talked about. Now come to the next, that is method of image and its application. We will start with method of images and its application. Right? So what is method of images, right? Do we need to follow this? Is this a law or is this a rule? No, this is simply a trick, right? This is simply a trick to obtain the potential of a system, right? By mean potential, we refer to as the electric field also, right? If you know the potential, you know the electric field, you can find out the charge configuration also, right? So I guess if I'm saying potential only, you can realize, okay, if you know the potential, we can find the electric field, we know these relations, and if we find the electric field, we can talk about the charge configuration, right? So this is basically a trick to find out the electric potential. Now, how this trick is valid? Remember the first uniqueness theorem, right? Remember the first uniqueness theorem, right? The one of the corollary, or if we interpret this first write this. If we interpret this first uniqueness theorem, we can say that if for a reason, right? If for a reason, uh, we have a charge configuration, or if for a reason, if we have a hypothetical that doesn't exist, hypothetical charge configuration that satisfy boundary condition, then the effect of that charge configuration, will be similar to original one, right? Why? Because we know that if you are using the Laplace equation, right, Laplace equation with boundary conditions, right? If we have to solve the Laplace equation with boundary condition, it will give unique solution. Unique solution, that means one and only, right? We can reverse this thing, right? If we solve this Laplace equation with these boundary condition, we will get what? A unique solution, that is one and only solution, right? If by any trick or by any means we can get this solution such that it satisfies these boundary condition, right, then the process or the trick or the method is correct, right? Try to understand this thing, because see, if I tell you how to solve the question, you can solve this question, but these things are very necessary when you're writing the introduction as well as the conclusion. What is the idea behind it? It's not a law, it's not a theorem, it's not a formula, nothing. It's a trick only, right? It's a method, it's a trick that we know that we have to solve one equation, right? Let's suppose we have to solve one equation and it will have only one solution, right? Now reverse the solution. If you can find the solution, then we can say that it is the solution of the first one, right? So if this boundary solution will have only one solution, and by any means if you can find this one solution which satisfy this boundary condition, then that method is true. And same is the case of the method of image. Now see, does it mean that the same configuration is valid for all over the space? This is no, right? This, because in the conclusion or the limitations of this method you should also know, right? This method may not be true for all space. Maybe what I'm trying to say, let's suppose if we have, this is a quadrant system, right? Maybe it can happen, it can valid for first one, but in third quadrant it failed to obtain, right? So for the first quadrant only we will say that this method work, for the third quadrant this method don't work, right? So if we replace, if we have this charge configuration and if we uh, exchange this charge configuration with this, let's suppose, right, and the result will is only complying with the first quadrant, then we can say that the only the in the first quadrant only the we can use this method. For the third quadrant we cannot use this method, right? So if you are clear with these things, let us jump to the classical image problem, right? and this will clear your doubt, right? As well as how we can use this thing. Okay, and also what are the limitations and what are the physical quantities we can extract from this method, right? So what we are given with a conducting sheet. This is a conducting sheet and it is grounded, and we have a q charge here. This is conducting plate, right? So what does this mean? That is, the potential is zero here, right? Here it is a charge, and let's say this is at a distance d, right? And we wish to find potential here, right? If we wish to find potential here, right? Now if we make the coordinates, right? Let's make the coordinates. Okay, so this is the coordinate here. This is x-axis, this is y-axis, and here this is z-axis, right? So we need to find out potential at z greater than 0, right? So above the conductor. So we need to find out above the conductor. So this is our case. This is our problem basically, right? So we have a conducting plate. The potential at the conducting plate is 0, and we wish to find out the potential at above the plate, right? Now, how will we solve? So we can use Laplace equation. This will always valid. Right? This is always valid. We can use this, right? And it will give one solution. Give one solution, right? And which satisfy some boundary condition. For example, the first boundary condition is v equals to 0 when z is 0, right? Means on the conductor. On the conductor, the potential is 0 there, right? Now, second thing also, that v tends to 0 when r square is much greater than d square, right? R is the position where the, sorry, the point is given, where r square is what? R square is equals to x square plus y square plus z square, right? These two conditions. Now, so this solution will be unique, one solution only, unique solution. And by any means, if we can get a solution, right? If I can get a solution that satisfy, so we will use any trick, and this trick will give us one solution. And if this solution satisfy this equation, then this solution will be accepted. And this is the idea behind the method of images. Now, what we will do, this is our conductor, this is our conductor, and here the charge at distance d. What we will do, we will replace this, right? Let me draw the coordinates, right? This is x-axis, this is y-axis, right? And this is z-axis. Now what we will do, we have to make here q is here at a d. Okay, now I assume, treating this as mirror, I will get a mirror image, right? Plus, so here I will get a charge, right? What should be the magnitude of this charge and where it should be placed such that at this position here, the potential is zero, right? D above, D down. If we can consider D down and minus Q here, we can say that the potential will be zero here, right? Because this Q is also equal distance and this minus Q is also equal distance. So here what we can do, KQ by D minus KQ by D will be zero because scalar is a potential. Sorry, potential is a scalar quantity. Now, understand. So what we have done, we have just replaced this configuration with this configuration, and this is like the mirror image. That's why we call it method of images. Now, understand one thing. Is it satisfying all the conditions? Yes, it is satisfying. Because if we want to find potential at any x, y, z, what we can write here? Let's suppose this is a point x, y, z, right? So r plus and r minus, I can write it. So it will be 1 upon 4 pi epsilon naught q upon r plus minus q upon r minus, where r plus is the distance of that point from the positive charge, or you can simply write it as 1 upon 4 pi epsilon naught, right? What will be the coordinates in terms of coordinates? So this is basically 0 comma 0 comma d, and this is basically this coordinate is 0 comma 0 comma minus d. So it can be simply written as q upon root under x square plus y square plus z minus d whole square minus q root under x square plus y square plus z plus d whole square, right? Here also v tends to 0 as uh, x square plus y square plus z square is greater than d square at a larger distance, at infinite distance, right? So it is applying both conditions, right? So whatever the potential due to this charge, we will assume, right? So we will accept this. Why? Satisfying our boundary condition for z greater than 0, right? If you talk about what happened for z less than 0, right? If z is negative, is it the same or not? So it is not the same, right? For z less than 0, it is not the same, right? So but do we care about this thing? No. Why? We have defined this configuration for z greater than 0. So if you are having any problem, you can see this. See, plus q is here, minus q is here, and if we have 2 points, right? 1 point here and 1 point here, right? So the potential at any point above this plane will be dominated by this one, and the contribution of minus q will be less than the plus q, right? Because it is nearer to this one here, but here it will not be the case, right? So understand, when you are using the method of images, it doesn't say that the same configuration will have same effect over all these ways, no, right? But same configuration will have the same effect over a certain region, right? So same or the new configuration will have same effect in some region, not in all space, right? It may be true in certain cases, but generally it is not true, right? Now, so what we can take out from here? So if you are given that this is the conductor and it is grounded and you have Q and this is D, find out the potential at any point where coordinate is X, Y, Z is given, right? So you have the answer. What do you have the answer? 1 upon 4 pi epsilon naught Q upon root under x square plus y square plus z minus d whole square minus q upon root under x square plus y square plus z plus d whole square, right? So this was our problem to find. Now you can see finding out the potential using the method of measure is much simpler than solving the Laplace equation, right? You can see just you have to do what you have, just replace this configuration with a q and a minus q, right? This is at D and this is at D, right? Now we are having two questions. We talked about limitations, right? Yes. Not valid in all space, not all physical quantity can be determined. Example, energy. You can find out the potential using this thing, but if you say that energy, if you can find it out, no, you cannot find out the energy, right? So what are the things we can find out? So method of images, you can find out potential, okay? You can find out electric field, yes, right? You can find out induced charge, yes. What is induced charge? I will just tell you in a while. You can find out force, right? But you cannot find out energy, because energy is a real thing. I don't mean that all of the things are not real thing, but energy depends upon the position here, right? The distance between the configuration also. Okay. Now, how to do this? See, these are not something that come from a law, right? These are some observation, mathematical calculation, tricks, techniques that you have to accept it, right? How you have to accept it? What is the rationale behind it that we have talked about? Now, let's talk about induced charge. Right? So, if you remember, if you have a conductor, right? I mean to say conductor of any shape, conductor, any shape, and if it has a sigma as what sigma as surface charge. You have studied in your engineering classes also this thing. So a point near point near the conductor, the electric field can be written as sigma upon epsilon. Right? I guess you know these things, right? And E is what? E is minus del V by del R. E is what? Minus del V by del R is what? Sigma upon E naught. So if you want to find out the induced charge, sigma will be what? Minus E naught del V by del R. Right? This is induced surface charge here. Why here? Because conductor having no charge, right? So we are having a plus q charge here. So due to the plus q, here it is induced. right? How the induction process work, I guess you know these things, but let me brief it, right? So let's assume that induced charge is sigma, right? So here in z direction, what we can write here? Let's take this direction. So sigma can be simply written as minus E naught del V by del Z at Z0, because this is at where the conductor is placed, right? So del V or del Z is given there, right? If you wish to find, you can find it out, right? So del V by del Z will be equals to, oh no, you can find it out. I have the result, right? I'm just writing out the result. I guess you can find it out easily. So sigma will depend upon minus cube d 2 pi x square y square plus d square. Okay, this is the induced charge. I guess you all know how to partially differentiate equation. We have done it multiple times, right? So now this is what we have decided here. If this is the conductor, right? So it is lying in z equals to 0, and we have bifurcated in planes, right? For x and y, right? This was x and this was y, right? So at any point for any x and any y, what is the induced charge that we have done here, right? But we wish to find the total induced charge. Q. How will you find? Just integrate over the area. So Q will be what? Sigma into dA. dA is what? Sigma into dx into dy. Simply. Right? Now let's move this Cartesian coordinate to polar, because it will be easier, right? So we know that in Cartesian to polar we can write that x square plus y square is equals to r square, right? Dx into dy is basically r dr into d theta, right? R dr into r d theta, or d phi, whatever you want to say. Simply put this value. So sigma will become the function of r. It will equal to minus qd 2 pi r square d square 3 by 2, right? So q will be equals to minus qd upon 2 pi r square plus d square 3 by 2 into r dr into d theta, right? What will be the limit of r? First we are integrating with the r, so r will be positive, right? Understand, whatever we have introduced the electric field or whatever we have talked about is for the z greater than 0. So be careful while writing the limit of this integration. So it will be 0 to infinite, and d theta is again complete 0 to 2 pi, right? If you will do this, it will equals to minus q, right? So q equals to minus q, right? Total induced charge will equals to minus q here, right? If you know the basic of conductor and the induction, you will come to that, okay, if it is the conductor, then the induced charge will be minus q only. Now if you have any problem, just put r square plus d square is t, right? And you can do the stuff. So 2r into dr is equals to 2r dr dt, right? So we'll put these values r dr barabar dt by 2 here, and this will what? T to the power minus 3 by 2. You can solve it easily, right? So I'm not going into these things. Now I was talking about induction. What induction is basically, understand, if this is a conductor or any even in dielectric induction, appears. And if we have a charge here or any electric field, right? So this charge will have electric field, right? Electric field. And what we do, these electric field, let's suppose it will have electron that can flow, right? What happen at a certain point of time, this electric field attract these electrons. So here number of electron become more as compared to this side. So we'll say that this part is become negatively charged. Overall charge is again 0 and this one is become positively charged, right? And if you induce it to the earth, then it will what? Carry the extra charge and will make it charged, right? Now understand this thing. Say, I guess you know understand these things, right? So if Q is here, right, and if you have let's say D, and this is R is here, and this is Earth. Now let me ask you this question. So will there be any charge induced in this sphere? So you will say yes. How? Because on the surface of this sphere, you have to put it 0. So you will write, okay, KQ by D is the potential due to charge at this point. For this point or at the potential, what is on the surface will be in the potential at the center, right? V at surface is V at center for a conductor. I guess you know this thing because electric field is not present inside the conductor, right? So KQ by D plus what will be, so let's suppose Q dash. So KQ dash by R is equal to 0. So from here you will find out the Q dash, and similar the case above, right? So to make the potential 0, this charge or electric field due to this charge will induce some charge there, right? This is the meaning of induction there, right? So here also, if the conductor was there and if it is placed at earth or grounded, potential was 0. But if you place Q here, then charge must induce here to keep V equals to 0. This is the idea behind the induction. Okay. Now, so using method of images, we can easily find the potential. We can easily find the charge also. Right now, is it? You can find the force. Yes. Force will be also what we have it. Plus Q is here, minus Q is here. Attractive force will be there, right? And distance will them is what? 2D. So minus 1 upon 4 pi epsilon naught Q square upon 2D whole square z cap. Right? So this is the force on this or force on conductor. Right? What is the nature? Attractive. Right? So whatever the force is experienced by this charge is equal to the force experienced by the conductor. Right? Now, if you have multiple charges, then whatever the new charges you have created, right? So I will write it here. Force experienced by the new charges is equals to force experienced by the conductor. Then actually these charges were induced inside the conductor, but we are taking an analogous, so we are taking any trick. That's why. Now, force is this much. That is sufficient. But what about energy? What about energy? Is it, we can evaluate that plus q is here, minus q is here, and distance between them is 2d. Can we write uh, the energy is equals to minus, or energy, or whatever you can say, work, anything. Energy is 1 upon 4 pi epsilon naught uh, plus q into minus q, so here will be minus q square by 2d. Is it correct to write or not? So this is wrong. Why wrong? That you have to see, right? So when, what is happening here, what is this energy, right? What is this energy comprises of? This energy is comprises of bringing both charges from infinity to this position. So we are bringing both those charges from infinity to arrange this configuration. This is the meaning. So this is the case here. Now understand what will be the case in reality. So this is a conductor, this is held fixed or simply not moving, right? And we, this is q at t, right? So here what is happening here? Bringing only q from infinity to this point. Here what we are doing, bringing q from infinity to this point only. Now understand one thing. You will say that some of these charges induce here also, right? So will they move? Yes, they will move. When the force is between them, they will repel each other. But here V is 0. So the energy in the movement of these particles will not be counted here. Right? So here what will be the energy? We can simply write it using the formula, right? So work done can be simply 1 upon 4 pi epsilon naught, right, into q square upon 4 z square dz from infinity to d, right? This is what we are going to perform the work. So this will be equals to 1 upon minus 4 pi epsilon naught q square 4d, and this is half of previous. This is half of previous, right? So this you need to understand, and this you need to write wherever in examination it is. So be careful while writing method of images, right? So for method of images, you can find out potential, you can find out induced charges, you can find out force, but be careful while you're writing the energy, right? This is all what I need to say. Now can we solve? Okay, this question comes in 2003, 4, 8, again in coming 10 also, I guess. So this again, the classical image problem comes 4 to 5 times in the examination itself, right? Now, nowadays UPSC is not asking this type of question, but a similar type of question is this, that they ask in 2020. So this is the question. Okay. This is the question. This is asked in 2020. Now, this is for 10 marks. How, what you will write in introduction? So you will talk in introduction. What is method of image? What is method of image? What is method of image? So basically, method of image is a tool or technique to find out the potential in a region due to the configuration by converting the original configuration to a mirror image with respect to the conductor, right? This is basically method of image is, right? And it is based on the principle of uniqueness theorem that says that there can be only one and only one solution that can satisfy the given boundary condition, right? So these things you can write in the introduction, right? So method of images, and you have to talk about the uniqueness theorem, you have to talk about the Laplace equation, right? All these things should be done in 3 lines, 3 to 4 lines. Now, what should be in the conclusion? Here also, above part it will work. For the down part, it will not work, right? So these things you can write in the conclusion, or whatever the solution we will get, you can explore that solution or explain that solution. So I'm just telling you how it is. So we have to maintain potential V0 here. So how will we change the configuration? If this is the conductor, let me use this. This is the conductor, plus Q is here, minus Q is here. This is at D, this is at H. So what I will do? At a height H, I will place plus Q so that this will balance this one, and I will place minus Q, which is will be D distance above, right? And potential finding due to these 4 charges is very simple, very easy, right? So you can find out the potential. If you can find out the potential, you can find out the sigma, that is minus E naught del V by del Z at Z equals to 0 here also, right? So this is your homework to find out. You can find it easily, right? For any x, y, and z, you know the distances, right? Just write the potential due to them. Potential are scalars, so you need not to worry more, right? You can also find out the forces between them, right? So this is what. So P is given here, right? P is dipole moment. So this is equivalent also to this dipole. So we are having one dipole P here, and distance H. Here you will have P, right? But you will consider this distance, right? Center to center. That will again, it will be H plus D. So don't use H plus D, and you have to work between these two dipoles, right? So if you can find out the interaction between two dipoles, which is separated by a distance H plus D, you can solve this question. So in coming section, we will study about dipole and how can we find the interaction between dipole, right? The main takeaway from the method of images is that we are able to convert this configuration into this configuration, right? This is an easier configuration. Come to one more question, and this is very important question. This is solved in each and every book. So let me write out this equation about this problem. So this problem is that we have having, this is a uniform this is a uniform sphere, right? This is a uniform sphere, and radius r is given, okay, and from the center at a distance a, and with the center we are having a charge q, right? Okay, this is given. So a charge q is situated at a distance a from the center of a grounded conducting sphere of radius. Okay, this is grounded also, right? find the potential outside the sphere. So at any point here, right, at this position, we want to find out the potential. Right? Now, if I can make you arrange in a fashion that what is the configuration, right? What I will do, I will help you to find out the equivalent configuration, and rest you can do this. Equivalent charge configuration. So we need to find out the potential here. We at this position, right? Can you find it out? Now you will thinking, how can we take the mirror image now, right? So what I will say, that let's assume that this is the center of this one. This is solved in each and every book, right? This is the sphere. Okay, cool. Okay. Now here we are having plus q, right? And this is at a distance a. Now let us imagine a point here, right? And q dash will be there, right? And it will at a distance b, right? This distance is r given, right? So this is at a point b. So I'm just explaining this configuration as that this is the center, and from center at a distance b we will having a q dash, and we are having a charge q at a distance a from the center. Now if we can find out q dash and b, can you find out the potential at this position? You can easily find out, right? How? So if you have two charges, right, one is b from center, one is a from center, so you can easily find out the potential due to two charges, right, at this position, right? You will find the potential at this charges, at this charge, and you will sum both of these, right? Now how can we find out the values of q dash and b? This is a much larger question than the question itself, right? So we will see this one. So here also what we need to do, here something we need to apply. We need to apply the boundary conditions here. These things have to. So these are the surface and v is 0 here, right? So I will take 2 points, right? This point and another point is this, directly opposite to this point. For the calculation to be easier, a and b point, let's call this a and b, right? And if v at a is 0, right? V at a is 0. That simply means what? 1 upon 4 pi epsilon naught q. Let's call this as q dash. This is q dash, right? So what will be this distance? R minus d, I guess. So let's write it for this q. What is this distance? This is, I guess, a minus r. Yes, a minus r. Okay, why I'm confusing it. Plus 1 upon 4 by epsilon naught q dash upon this distance. This distance from here to here is basically r minus b, right? One condition is this, because the surface is at 0. From here what we can take away, that Q multiply these things and we can find it out that Q इधर चला जाएगा equals to Q dash. So Q R minus QB, right, is equals to Q dash R कहाँ से आ गया छोटा? This is capital R, right? The radius. Right? QR minus QB. Is it right? क्या हो रहा है? Okay, QR minus QB, is it correct? Yes. QR minus QB is equals to Q dash R, because minus will be gone there, minus Q dash A. Yes, this is one equation. Okay, now what will happen? VB equals to 0, right? So at VB equals to 0, the distance will become A plus R and R plus B. 1 upon 4 pi epsilon naught Q upon A plus R plus 1 upon 4 pi epsilon naught Q dash upon B plus R is equals to 0. Potential due to them is 0 on the surface. I'm just taking the positions, right? You can take any arbitrary position, but it will make your equation lengthy, right? So this will be what? QB plus QR is equals to Q dash minus, again here it will be, so minus Q dash R minus Q dash A. सही है. So these two equations are there, right? Equation number 1 and equation number 2. Again, so what I need to find out, Q dash, if I add both, what will happen? Will it eliminate B? Yes. Adding both, what happen? If I add both, QB and QB will cancel out. Here we will having 2QR is equals to Q dash R will gone, minus Q dash A, minus 2Q dash A, right? So 2 cancel out. So from here Q dash is equals to minus RQ by A, right? This is what we are waiting for, right? Now we want to get the B. So what we can do? Subtract 2 from 1, right? We will subtract 1 from 2. So if you subtract 1 from 2, QR cancel out. Here you will get 2QB, and this is equals to क्या आएगा? Q dash A will cancel out, and you are left with minus Q dash R, right? Minus Q dash 2Q dash R. So 2 again cancel out. So QB is equals to Q dash minus Q dash, so minus RQ by A. So Q is looking like A and A is looking like Q here, but this is not the case. Minus RQ by A into R, right? So Q and Q cancel out, minus minus goes plus, and B is effectively equals to R square by A, right? Now we know the Q dash, we know the B. What we know, right? Let's suppose this is center 0 comma 0 comma 0, right? Here is Q dash, which is at a distance B from this. Anywhere you can take it, and here it is at a A, right? You can take R theta coordinate, whatever you want, whatever the question is given, right? And this is A, right? So we have find out B as well as Q dash. So at any position we can find out the potential, right? And it should be done easily. Okay. So this was, now how can we calculate the force, right? So force between them will be simply equals to 1 upon 4 pi epsilon naught, right? Q dash upon A minus B whole square, right? You know the value of B, you know the value of Q dash, just put it here, you will get the answer, right? Q, A, all are given already, right? So this is a very easy method to use, but again, be careful while using this method, right? Sometimes it didn't get the result. So let us solve one question, one more question again based on this. So I guess you can find out these questions. Some questions are relatively that we will find the conductor and they will say some charge is here, some charge is here, right? Some charge is here. So what will do? You will make the mirror images of these things, right? For example, okay, let me put this question. This is a very interesting question. So if you have two conductors, right? No, let's suppose both are grounded, right? This is also grounded and this is also grounded, and you are having a charge q here, right? And let's say this is at a distance a and this is at a distance b, right? What will be the effective configuration of this one, right? What is the effective configuration? If you can find out the effective configuration, then finding out potential is a cakewalk for you, right? See, if I can say you that these two conductor and one discharge, you can replace it with some certain amount of charge, then it is very easy. So I don't know how many of you have studied in optics or not in your junior classes, that these perpendicular you will get one image at B, this one image at this point, and one image vertically here, right? So you will get three images here, right? So again, this is minus q, this is minus q. What will be the nature of this one, right? See, that we have to see. Why? These two things will balance each other, right? See, you again, you should know some basic of optics, right? So this is if you know that something 360 degree by theta minus 1, right? Something as a right, number of images in junior classes. Some of you might be teaching for ITJ NEET also. Some are also there enrolled are teachers, so they can visualize easily. So again, understand these two are mirror, right? So if these two are mirror, you can find the mirror images, right? So one for this one and one for this one, and again here also image will come, right? Why? And what are the distances? First, let me write out the distances. So again, it will be B, it will be A. What will be the distances of this one, right? So if I extend this as coordinate, right? So This will be B and this will be A. Now what is the sign of this one? Again, understand, come to this point. So here we have to keep the potential at 0. So this will be balanced by this minus q. But due to this one, a potential will be there. So here we should have a plus q charge, right? So this configuration, we will get same result. Let's suppose here you will want to find x, y, z. A position is given here, right? This is x axis, this is y axis, right? You are given with the position, right? The coordinate is what here? A comma b comma 0. Let's say here what will be the position, right? This is again a. So a comma minus b comma 0, right? Here also minus a minus b comma 0. Here what is the position? Minus a comma b comma 0, right? The coordinates you are given with, you can easily find out the potential at this position. If you cannot find out, then you seriously need to check your basics, right? Go and check the 12th class any book. So here minus q, here q, here again minus q, here again q. So these four charges are there. If you can find out using these charges, this is very easy, right? So whatever the charges is there, you can find it using this. Okay, now again similarly goes with the line charges, any configuration. You just have to take mirrored images. See, two conditions are there. V is 0 at conductor. Basically they will give you this question only, right? For any larger configuration. And again V 0 at infinity, right? If any configuration your mirror image is in accordance with these boundary conditions, then it will be helpful, right? Now we will solve one more question and then we will move to the another one. This is very important. This is also very important because this can be asked, although it's a very tough question, it should not be asked, but it can be asked. So the question is, where the question is? In example 2, but addition second charge is any potential V naught. Okay. हाँ, देखो. Again, the question is that we will give you same question, that this is a uniform sphere. Okay, sphere is already uniform. No need to write sphere is uniform, right? Charges. But still, uniform sphere is given. The V is not 0. It's V naught already. Right? V is not 0. It is V naught there. Okay. And force of attraction between a point charge Q and a neutral conducting sphere, right? And a neutral conducting sphere. Okay, what does it mean? So पहले क्वेश्चन लिख लेंगे. This is Q. Okay, this is these some most of the from the Griffiths only, right? So you need not to solve the Griffiths on your own, right? Whatever the important questions I have already done here. Even the previous year question, the classical image problem has been asked 4 or 5 times. The plane wala question, inclined plane, we have done already, and the dipole, right? So we have done all the previous important questions, and we have done all the important questions that is given in the Griffiths also, right? So this you have to revise multiple times only. Now V equals to V naught, R is given, Q is given here, right? And what they are saying, find out force of attraction between point charge Q and neutral sphere. How can this sphere be neutral? It is already having a V naught, right? See, if it is not there, if it was not there and it is not earth and it having a V naught potential, then it cannot be neutral, right? But as we have introduced this charge, it will induce some charge there that it will make it as a neutral, right? So first, uh, so if it is a neutral sphere, right? What we need to do, we will again assume this thing that we are having a charge q here at a distance a, and due to this charge we will have an induced charge, that is q dash at a distance b, right? And we will again put here let's say qs, that is the charge on the sphere. Why I have put it there, right? If I put the charge at the center of the sphere, right, it will not make it as equipotential surface, right? It will uh, not center equipotential will be maintained, okay? Or see, understand one more thing. Whenever you are given with a conductor, right, it is equivalent to put assume it like that is charge is at the center, right? There is no need to do the further phd. So if you study conductor, you can say it easily, right? So what I have done, we have placed qs at the center, right? So that it will not affect anything, right? But what will happen if qs was 0, v was 0, no earthing is there, no outer charge is there, right? But if v equals to v naught and qs is not 0, then we can establish relation, that is kq by r is equals to v naught. I think you know that. That is v naught is equals to k. Let's write it down. The value of k is what? 1 upon 4 pi epsilon naught qs by r. So from here we can find out the qs easily, because we are given with v naught 4 pi epsilon naught r v naught, right? So we are done with this question. We are having above charge configuration can written as, we have a charge q here, we have a charge qs here, and we have a charge q dash here. This is b, this is a, right? And we already know the value of q dash from our example and the value of b, right? So now let us find out the force, right? So the force I'm just simply writing the force wait a minute, I'm facing some problem here. So simply I will write down the force, and it's your homework to put the value. So simply, what will be the force between this neutral sphere and this charge? So this force will be mainly, what should I do? This force between neutral sphere and the charge, right? Let's suppose sure, is basically the force due to qsq plus q dash q, and that is equals to 1 upon 4 pi epsilon naught, right, qs into q upon a square, right, and plus 1 by 4 pi epsilon naught q dash q upon a minus b whole square. Now it's your responsibility to put the value of b, q dash and qs, right? Qs value we know that, right? Again also we know the value of b and q from, right? So now we will start with dipole and dipole moment. After the basic introduction or completing the dipole, we will study the multipole expansion of the potential and also will relate these two terms, right? But first we will see the dipole and dipole